Brian recently joined Virsto. He's not one of our founders. The other founders are here in the room as well. There's Alex. Brian joined us recently from EMC, where he was doing a lot of advanced development work on a whole bunch of projects. Brian is old enough to date his lineage at EMC through a little company called Data General. For those of us who remember Data General and what they were. Brian worked. Anybody remember Numa? Who remembers Numa? Okay, that was awesome. Brian did Numa work at Data General back in the days when Data General was doing interesting stuff in the late 80s and the early 90s. So I'm going to hand it over to Brian. He's going to walk through the technology, and then we've got some other secret stuff that we're going to talk to you about in the future. So thanks for your time, Brian. You're on.
Well, you walk up there, Brian. I have to warn you, I'm a giant Avion and DGUX fanatic, and used 6600s. And, yeah.
Okay. Thank you. So I'm Brian Martin.
I used to have Nova 4 in my basement.
Excellent. I joined Virsto in the last few months from EMC and Data General before that. I have a long history in scalable systems, servers, Numa, storage. I've done a lot of scalability work on both data warehousing side, transactional side. Ran partner engineering for a while, working with the likes of VMware, Microsoft, Oracle, SAP, a bunch of other small companies, trying to get this stuff to actually work at the customer site. So came over to Virsto because a lot of what you've heard from Mark is a lot of what I was seeing as well. You know, there's a fundamental change in the nature of storage for virtualization. And quite frankly, these guys got it right. So I'm happy to be here, and I'm going to talk about what we do, how we do it, and some of the cases why we do it. So let's jump into it. Slide changer left.
She only works for the CEO.
I guess so. All right.
It's okay, Greg will come do it.
So fundamental, we got some of this earlier, right? It's about the software. You know, you've talked to a lot of storage companies. You've talked to a lot of storage hardware companies. And they will proudly tell you that 70, 80, 90% of their employees work on what? Software, right? They're not hardware companies, they'll tell you. And the fact is, the differentiation in storage is in the software. So Virsto takes that to another level and says, in the virtual data center, why don't we put the software where it can be most effective? So this is software only, hypervisor resident. The right software at the right level to solve this impedance mismatch between data and storage. It's fundamental to what we do. It's also about the VM, and it's about the vDisk. The unit of storage is not a LUN. A LUN is a very uncomfortable and awkward unit to work with in this virtual world. A lot of nods here. You know, we spend a lot of time trying to coordinate that. You know, don't want to go past 255. What do you mean you need 10,000 of these little storage things? I can't make 10,000 LUNs. Or if I could, I really don't want to. So we've got to treat that at the vDisk level, the VM level, and work from there. It's got to be agnostic. So the part about software, this is exactly what VMware did. You know, I love the phrase Mark used earlier. He said, the #1 server company doesn't sell servers. The most important server company is VMware. It's a software company. And that's because the underlying hardware is agnostic. It could come from anywhere. The same is true in the software-defined storage world. It's got to be agnostic, hypervisor agnostic, storage platform agnostic. It's got to be high performance. Data services. Data services are really where it's at. We look at software-defined storage, and it became very obvious to us quickly that software-defined storage is as much, if not more so, about the data than it is storage. Okay, why is that? You know, we look at virtualization today. Virtualization on the server has been very successful because CPU and memory have become extremely fungible commodities. It's very easy to move around. One CPU cycle is as good as another CPU cycle. One memory cycle is just a context switch away from another memory cycle. When you get to storage, it's like you run into a brick wall. Everything gets harder, everything gets slower. Why is that? You know, and the reason for that is while CPU and memory are very fungible, data is very viscous. You know, moving data takes energy. Moving data takes time. Moving data takes an appreciable amount of resources. So we have to think about this differently. We have to approach this differently. So as we deliver these data services, caching, replication, snaps, clones, encryption, deduplication, we have to keep in mind that we can't just arbitrarily use moving it around as an answer, because moving it around is expensive. More cores is good, but a funny thing happened on the way to the store. Way back when, you may remember the Clarion CX3 family, 340, 380, lovely set of products. The 340 wound up being the sweet spot in that lineup because the CX380 was architected for a 5 gigahertz processor that Intel never shipped. It created a little bit of problems back home.
Whole day, couldn't it?
A bunch of days. And what happened was that we know very well, I know very well, when the industry shifted from scaling up to faster processors to scaling out to multiple cores. Because I was running a performance group at the time and working on partner engineering and application solutions, and the whole world just took a step sideways on that day. And that's continued. You know, there's a lot of processors today running at what? 2-point-something gigahertz on their cores. You know, that's half a decade when the top speed has gone nowhere. Okay? Scaling out, that's how we do performance. But we can't move things faster just by forcing them down the pipe, because the pipe doesn't go a lot faster. We just have a lot more pipes. So we got to keep that in mind. And lastly, as we scale the performance from clusters to clouds, is our phrase we like to use, those data centers can't be impacted. So these are the fundamental concepts underlying what we've done. If we go to the next slide, we can see how that impacts what we came up with. So first and foremost, these efficient data services. We talked about that. I want to talk a lot about the next bullet there. Highly parallel, independent, non-blocking architecture. I feel like I sound like a switch vendor, right? I got my InfiniBand, I'm Mellanox today, right? Non-blocking, high performance, it'll run anything.
Need the Hebrew accent.
We have folks. Can I get an accent here? Thank you, Alex.
Independent, non-blocking.
Thank you, Stephen.
The Hebrew accent, not the
Oh.
bad Austrian accents.
All right, we can do that one.
I am deep
It's
to the band name.
critical. The way we scale these environments, we've got lots of cores. We can't tie them up, you know, doing spin locks or semaphores. We can't tie them up trying to get to the same resources. And that's within a server. When you go to multiple servers, tens of servers, dozens of servers, how many servers can you put in a cluster today? 64, I believe, is supported. You know, on the mainstream side, you get off into OpenStack Linux, you've got hundreds of servers. You know, we have to have a parallel non-blocking architecture, and that architecture has to flow through all of those data services. We have to be able to see everything from everywhere across the cluster. That global namespace is important. Mark talked a little bit earlier about sort of a file system, clustered file system, a clustered volume manager, a little bit of each, some of both. What we want to talk to at the end is these virtual disks. What are virtual disks? Virtual disks are files. You know, one of the things we've discovered in virtualization, our customers told us this in virtualization, is they like the ease of use in managing files, and they like the performance of disk. So how do I get the best of both worlds? You get the best of both worlds by re-architecting the storage stack with virtualization in mind. And that's what we've done at Virsto. And we've done that through a logging architecture, not a transactional architecture. We've done that with flexible hierarchical maps that give us an incredible amount of flexibility in the way we move data around. So enough of the words, let's get some pictures up here. At the heart of everything is this vDisk. Again, what is a vDisk? A vDisk is a file that happens to contain an entire operating system and a bunch of applications. That file can be a VMDK file, can be a VHD file, can be a VHDX, soon it'll be a vvol. It could be an iSCSI right? Or it can be something on OpenStack KVM, QCOW2. I don't know why they came up with the worst acronym ever. With Virsto, our vDisks are this fundamental file, and they can be presented as anything any platform wants it to be. Huh, what does that sound like? That sounds like an abstraction. It sounds like virtualization. So what a storage hypervisor needs to do for data is what server hypervisors do for CPU and memory. This is what Virsto does. Here's your unit of data, and this is why I say software-defined storage is at least as much about the data as it is the storage. I'm going to spend half the time here just talking about data virtualization, but we're going to call it storage, just because that's what people understand. Once I've got it in that format, pivoting from one to another is easy. So if I want to have a software-defined data center, I want to be able to manage the economics. After all, the cloud is about what? Three things. Economics, economics, and economics. So I can take and trade off as I go through the life cycle of my applications, the life cycle of my VM, and I can take and move from one hypervisor to another hypervisor and do that pivot very easily. That's software-defined storage. Next slide, please. So I mentioned that the heart of the Virsto architecture here is this logging architecture. So what we see is multiple hosts. Every host for Virsto has its own log device, and that's where all writes are captured. So all writes coming through any vDisk on any host from any VM, like this. That's random I/O, by the way. This is sequential. This is random. Comes into the vlog and then gets destaged asynchronously out to vSpace. Does that concept sound familiar? Of course it sounds familiar. What have we done with that concept? We've taken it out of the array, moved it up into the virtual infrastructure where it can be more powerful, where we can take more advantage of those parallel cores, and where we can try to move data less. We have multiple tiers on the back end, so we can have SSD hot tiers, 15K RPM, 7200 RPM, anything else you want to throw at it. They can go high, they can go wide. Reads almost entirely come from the vSpace. Every once in a while you'll get a read that has to come out of vlog because it hasn't been destaged yet. That's fine too. We completely support that as well. Next slide, please. So Mark talked a little bit about the I/O blender. So we get these operating systems trying to do their individual optimization of their I/O streams, elevator sorting, whatever. We put 50 of them onto a host, and now they're all colliding again. What does that look like? That looks like these colored chiclets here. So these are the I/O coming down and arriving randomly in the vlog. And then when Virsto destages, one of the first things we do is take those intermixed groups that are all interleaved and put them back to the way they should be. So we untangle that blended I/O back into individual vDisk streams. We then do a couple of other clever things. Remove cancellation, coalesce where we can, and then we destage it to vSpace in as sequential a manner as we can to drive higher efficiency. So that vlog staging area allows us to do the untangling and the deduplicating of writes before they go back out to vSpace. All right, next one. Now, because we're vDisks and we're translating, so we have a block translation layer as part of that. You know, this is a fairly straightforward picture. Everyone should understand this. We've got a vDisk up there, different blocks go to different spaces, right? Any vDisk can use allocated space wherever it needs to, wherever it's assigned to, wherever quality of service points it to within the vSpace layer, and that's managed through our Virsto VMAPs. Next slide. Okay, this one's going to build. One of the cool things, we've talked about data services, snaps and clones being critical. Because all writes from all vDisks come into this log, the ability to take a snapshot at any point in time is as simple as dropping a mark into the log. So the writes arrive, they're ordered, they're just being piled in. At any point across any number of vDisks on the system, we decide we want to take a snapshot. Snapshot done. Okay? Across as many VMs, vDisks. That's an entire application landscape here. One drop. Anything after the log mark is not part of this snapshot. Anything before it is. That adds a lot of other interesting possibilities as well in more complex environments. You know, the ability to do a quick identification of a snapshot turns out to be very valuable in failure recovery scenarios. One of the things we've learned about storage over time, in fact, when I was working in the Clarion group, I spent a lot of time up at Microsoft when Microsoft was trying to do storage many, many years ago. And I sat down with a woman who was running a big piece of the storage infrastructure. She said, you know, Brian, storage is hard. I'm like, what do you mean, Catherine? What do you mean storage is hard? It's like, storage algorithms are easy. You know, any high school kid can do RAID algorithms. What makes storage really hard is the astronomically high cost of failure, right? Customers don't like when you lose data. And corner cases get really strange. Disk drives fail in odd and peculiar ways. So we've got to deal with that. We've got to manage that. So this ability to quickly identify what was safe, what was not, turns out to be extremely helpful. All right. Flash is, fill in the blank, ubiquitous, on the rise, coming, no, too late, it's here.
Magical.
Magical. Flash is everywhere. And Flash, quite frankly, belongs everywhere. Hybrid drives, you know, Flash right next to the platter, that's got its value. Flash in storage enclosures, Flash in the network, haven't seen a lot of that yet, but it's got its place there. Flash in the host. Virsto, you know, before we wrote a line of code, Virsto thought about Flash and how we can use Flash, and then we wrote the code and we waited. And how long did we wait? We waited years for today, where we can really take advantage of the crossover and the cost effectiveness of Flash. So Virsto's been designed from the ground up, not only for new ways of thinking about storage, but new ways about thinking about Flash and how to use Flash in dealing with these problems. So, you know, everything from the large numbers of snaps clones, right? One of the big problems, you talk about large numbers of snaps and clones coming off the same resource, well, pretty soon you're going to crush that common shared resource. If you're sharing blocks across 100 VMs, that's going to get crushed. Unless it's coming out of a very rapid piece of storage that has 30 microsecond response time. Flash, very valuable for that. vLogs. If we're doing all of these data services and they're built around the concept of the logging architecture, the ability to rapidly process the data in the log, whether you're, you know, ordering it, canceling out duplicate writes, deduplicating data, replicating data, being able to do that at very rapid speeds, very close to where the data originated, is incredibly powerful and very valuable. And then finally, at the lowest level, Flash is not rotating disk. You know, we're learning that as an industry. It's a shock. So,
I hadn't noticed that at all.
Well, you'd think that some of the storage companies hadn't noticed that at all.
Well, the place you used to work.
I can neither confirm nor deny what they believed about Flash.
I'll let you do that with Epiphany. Holy crap. This looks nothing like
this. Funny that.
Performance is totally different. Everything needs to change.
Move.
What do you mean it's completely asynchronous? It's unbalanced. You know, writes are an order of magnitude or more better than, or worse than reads. And by the way, this write cliff, right? It's Flash's equivalent to the fiscal cliff. Sorry. I'm not supposed to inject politics in here. These are real phenomenon. You know, the best description I ever got of flash memory is from a physicist friend of mine who said, imagine, you know, shooting a beam of electrons through a styrofoam cup and discovering that it remembered what happened. You know, it's a lot like that. Nobody really knows how this stuff works.
Wow.
We just know that it works.
That's way too good an analogy.
So you have to treat it differently.
Because it's going to
there you go. Feel free to use that. So they've got blocks they write, blocks they allocate. They've got these nasty things called erasure blocks or erasure block groups where you have to do these big page erases. The way we structure...
You get shingle disks.
Can you get vaccinations for that?
Yeah.
There's an ointment.
Excellent.
Yeah, chickenpox caused them.
So, being in this industry for a while, how many of you looked at SATA drives recently and thought, oh my God, it's the new tape drive? Excellent sequential performance, abysmal random performance. It's a tape drive. And then when you shingle it, you almost literally need to back up and rewrite. It's going to be like those tape drives sliding back and forth. Oops, we wore out the heads, or we wore out the motors. DLT, there you go. It's going to have those same phenomenon are going to show up in that new technology. So we've got to think about that. So the Virsto at the deepest layer, when it looks at blocks, it looks at data, it looks at how to allocate these things, takes into account not only spinning disk, but flash, erasure block sizes, which very conveniently laid the foundation for shingle disk drive technology. So all of these things need to be factored in, and they need to be factored in at a level where you can make a difference. Again, if I'm doing this at the operating system level inside the VM, and then I smash together 30 or 40 VMs worth, how effective is that going to be? Not very. So we've got to make sure that's not what we're winding up with. You have to do it where you talk to the I/O. That's at the hypervisor level in the new world in which we live. Next slide. Thank you. So what does that translate into? It translates into a lot of what I said here. Flash mode for vlogs, write amplification. Boy, there's a new phrase that we never had to deal with in storage. What do you mean a write generates a lot of writes? Oh, wait, that's called RAID. Different kind of write amplification, because now it matters because that static discharge in the styrofoam cup does eventually wear out. Being able to deal with data patterns, sort out data patterns, lay them down effectively makes a huge difference. Logs always written sequentially, big benefit. Sequentializing in the back end, big benefit. And of course, taking advantage of the sharing so that we're using the high-speed flash on those snapshots, on those clones. Next slide, please.